Okay, hello everyone. My name is Konstantin Bobrovsky. I am from Intel, and today I will talk about the project Andrew mentioned on his slides. This is Intel open source SYCL project. So basically, we are doing SYCL implementation, compiler, and runtime, and everybody is welcome to participate and contribute. A lot of work has been done, but a lot more of work is ahead of us, so everybody can participate. So this is a pretty short agenda. I'll provide some introduction to the SYCL language in more details, and then I will talk about the open source project. So what we are doing, what are plans, the architecture, stuff like that. And after that, we'll have time for questions and answers. Okay, SYCL introduction. So what is SYCL? So it is a programming language and platform for heterogeneous computing based on C++. And it has so it is also a single source programming model where you have host and device code in a single source, and it actually brings some benefits to the compiler. It is able, to do some more advanced things in terms of the optimization, type safety, and so on. But SYCL is built on top of OpenCL, and it basically provides you with the same kind of functionality OpenCL did, but probably in more convenient and productive way. But developers, of course, have a choice. They can still develop an OpenCL C++ kernel language, or they can start using SYCL. So basically, this picture shows kind of connections. So where SYCL sits in the software stack. So it sits between the user application code and the OpenCL implemented for different devices. So this is SYCL Runtime. I'll talk more on this. So by the way, okay, I need to put myself farther from the microphone. Can you hear me okay? Okay. So why SYCL? Reactive and proactive motivation. So even though OpenCL has a well-defined and portable programming model and execution model, it has some drawbacks, like somebody finds it too verbose for many application developers, and it mostly remains a C API, and only recently C++ was allowed as a kernel language, and it allows only for just-in-time compilation, which is sometimes not suitable for example, HPC usage models. And the proactive part is that we think C++ is a more productive language, and it is modern, and SYCL is based on C++. Yeah, so in future we would love to see some of the SYCL API and the programming model stuff to get into the actual C++ standard. And it is not held back by older standards which have their limitations, like CD99 or C++ 03. So just a small illustration. That's how you would write a small program which adds two arrays in OpenCL using C++ for the source code, for the host code. So it looks pretty neat, but anyway, you have to have two different sources. This is CL kernel code, which does the job, and here is the necessary oh, sorry. And here is the necessary host part. Now the same code written in SYCL would look like this. So the first difference is that it is single source, and you have your kernel code inserted right here. And actually, SYCL allows you to run your application even if you don't have any devices underneath. It can, so SYCL program can be compiled as pure C++ program, and it will run correctly. By the way, if anyone has any questions, please interrupt me and ask. So, yeah, SYCL retains OpenCL ability to easily target different devices in the same thread. And basically, you create a SYCL queue, and you select your device using special API class called GPU selector. So actually, GPU selector will select GPU device, and there is a general class device selector which you can use to implement logic of device selection. It's pretty flexible. So, this part is actually kind of defining your data, which will be used in the kernel, and here is the common group where you create accessors to the data. And those accessors actually create a graph, a dependence graph. So if you have multiple kernels and multiple buffers, and one kernels write to buffers, others read from them, SYCL Runtime is able to automatically detect all dependencies and schedule the work to preserve correctness. You can think of those accessors as kind of projection of those buffers to particular device associated with this queue. They can be another queue, and buffers, those buffers could be used in another queue on another device. That would be kind of another projection of those buffers. Okay, so, and finally, parallel loops are represented explicitly. You have a specific API for this, like parallel for, and you provide a range of over kind of ND range over which you want to invoke your kernel, and you provide a lambda with actual device code. So, looks pretty simple. Now, so I already mentioned about another difference between SYCL and OpenCL is that SYCL Runtime is able to automatically detect dependencies. So on this slide, you can see 3 kernels submitted into the same queue. But kernels actually have dependencies. Ad2 reads data written by Ad1, and Ad3 reads data written by Ad2. So there's clearly dependency between those kernels, but SYCL kernels are actually out of order. So you submit and you don't block, you go to the next statement in your program. So basically submission may complete before the first kernel even started its execution. But SYCL Runtime, looking at those accessors, will understand the dependence graph created, and it will make sure that Ad2 is not executed until Ad1 finishes. So that is done for you automatically. In OpenCL, you would probably use events to do that, and you could make mistakes, and sometimes you could like read data which is haven't finished writing. But in SYCL, if you get accessors right, SYCL Runtime will do the rest. Another example, it shows how 2 kernels which are not dependent on each other can be executed in parallel. So actually SYCL Runtime will guess correct dependence graph here, and it will schedule add 1 and add 2 to execute in parallel if there are underlying resources available, of course. And add 3 will be scheduled only after add 1 and add 2 have finished execution. Yeah, so here's a small remark that, so we'd love to have in-order queues as well, because that would simplify porting. Hopefully SYCL Next will provide us with that feature. Okay, and another interesting feature of SYCL compared to OpenCL, for example, is that this hierarchical parallelism feature. So basically, it allows you to explicitly define at least 2 levels of parallelism in your program. So for those who program in OpenMP, there is a OpenMP teams distribute construct with nested OpenMP parallel 4. This is kind of analogous construct. So we have a parallel forward group with 1 or more nested parallel forward item scopes. So everything which is in the parallel forward group scope and outside of parallel forward item scope is kind of once per work group. And the data declared here is shared across all work items. In OpenCL, you would use a local modifier, but here you don't need to do that. And you kind of intuitively write it here and expect this scope to be able to access this data, and that happens. And yes, and the code here is also executed just once per work group. And you don't need to write any guards, like if I'm a work item with local ID 0, I'll do this. So you don't need to do this with SYCL. So I find personally this very convenient way of writing parallel code. So any questions so far? So host code doesn't block, but it will block whenever you try to read a data. Like if you try to read output of add 3 in host, you create so-called host accessor, and that's where your program will block, because this is not yet ready. So it happens automatically. So, but if you don't need to read it at the moment, you can do other things, and whenever you need it, you just create accessor, and SYCL Runtime will make sure you wait until data is ready. Okay, so that was part about SYCL language, and now I'll talk about the open source SYCL project, which we started at Intel not so long ago. So first, motivation, why Intel started this project. So why SYCL? SYCL is an open standard, and it can target any device, basically. And it's also expressive and highly productive, so it should be very useful for people who need a float to different devices. So you can write your SYCL program once and offload that program to any compatible devices. Why open source? Because we want to promote SYCL as a programming model for offload, and to foster collaboration and innovation in the industry. So everybody, as I said, is welcome to participate and contribute. I will, later in the slides, I will show some of the topics, upcoming topics, which we will work on. So there's lots of work. Location information. So basically, we did a fork of LLVM on a GitHub. So it's Intel VM repository, SYCL branch. And our kind of final goal here is to contribute this back to main trunk of LVM. And you can see here the RFC for this. So some of the changes actually have already been committed, as shown here. And we have a plan for upstream, which you can check out here. Okay. So this slide shows what we actually, what we already did. So as I said, yeah, we are based on LVM and Clang, and the main changes are in those categories. So first of all, of course, it is SYCL Runtime, which contains some core runtime components like scheduler, like program and kernel manager, memory manager, and so on. And also, a big part of this runtime is SYCL API definition, which is pretty broad, and its implementation. Another thing is compilation driver. We did lots of changes there to support, this single source model, and to kind of, you can invoke just one single compilation command and build entire SYCL application with device code embedded into the resulting fat binary. I will talk a bit more about this. And also we support separate compilation of the device code as well, not only of the host code. And yeah, AOT compilation is in the works right now, ahead of time compilation. Next is front end. So in the front end, we added device compiler diagnostics. So basically, SYCL as a language has restrictions on what subset of C++ you can use inside kernel code. There are some like advanced, like some features like exception handling and direct control flow, which now is not allowed, and front-end diagnosis those kinds of errors if it meets it in the kernel code. We also did device code marking and outlining. Basically, we do some transformations. So whenever we see a kernel, we do some transformation to create actual kernel code, which is then passed to the backend, so to say, device compiler. And address space handling, and we have this integration header concept, which allows to use any third-party compiler compatible with C++11 as the host compiler. Tools. A couple of tools are used in the SYCL compilation process. First one is Clang offload bundler. It is probably familiar to those who did OpenMP offload. So basically, it existed before, and we extended this Clang offload bundler to also handle SYCL offload kind. And we also added support to enable fed static libraries, which means those are normal static libraries where each object contains, which object is fed, so to say, which contains host code and device code. And you can link those fed static libraries with your application code, just like you normally do with your host code alone. The next tool is Clang offload wrapper. It's a new tool. Basically, its function is to take multiple device executables and wrap them into a host object file, which is then passed to the linker to create final fat binary. And in OpenMP offload, in open source, they use OpenMP. They use linker script to do that actually. the linker script is passed to the linker to create the final fat binary, but that is not portable way because linker scripts is not supported by Microsoft tools. So we think and we hope that this approach will allow to implement this on Windows as well. And finally, we added a new environment to the spur target to customize behavior for SYCL compilation. Okay, any questions so far? Yes.
Anything on debug side of the equation here too?
Debug, yeah. So,
Can you repeat the question? Microphone. Is there anything on the debug side of the equation here too?
is there anything on the debug side of the equation here too? Yes, we do support propagating debug information to SPIR-V. Okay, now a series of architectural slides which will show a little bit more details about our implementation. So this is a compiler architecture. So left-hand side, you see SYCL sources, and you can see SYCL headers currently based at top of OpenCL. Here is the device compiler, or multiple device compilers. Here is the host compiler, and yeah, the host compiler is actually usual C++ compiler, so that's why it's just a black box here. But device compiler, basically, it can be invoked either in the JIT compilation mode, like kind of normal mode, when we produce SPIR-V, and it also will be able soon to invoke backends in ahead of time compilation mode to produce actual native device code. Actually, and there is another component in this compilation flow, integration header generator, which is actually Clang invocation, separate Clang invocation, which provides some details, not some, but all needed details for host compiler to be able kind of to bind to particular kernel, to generate invocation code for this particular kernel. So this integration header is fed into the host compiler, and finally we produce so-called fat binary, which is a normal host binary with device code embedded in it, and that then it is passed to SYCL Offload Runtime, which is able to extract either SPIR-V or device code and run it on the device or devices. You can see here dotted line boxes. This is still missing in our implementation, but it shows a path how SYCL could be implemented for CPU at top of OpenMP. It's similar to what Xilinx did with SYCL project, but we don't have this currently. Okay. Yeah, and as I said, we do support separate compilation and linking, and I will show on the next slide. Any questions with regard to compiler architecture? Okay, so this is an illustration of what happens behind the scene when you compile your SYCL application. So here at the top you have your sources, which contain both host and device code, and they of course use SYCL runtime headers. What happens here is we have actually 3 pairs of invocations. 2 invocations of device compiler middle end, 2 invocations of integration header, and 2 invocations of host compiler. This is all done by the compilation driver actually. So first of all, device compiler middle end, it takes those sources, extracts a device code from them, generates kernels, and produce bitcode files out of those LVM IR bitcode files. So initially, we generated SPIR-V here. And we wanted to generate SPIR-V here, but it turned out that SPIR-V toolchain and format is not kind of fully suitable for that purpose. Because, for example, a lots of functions are defined in the headers. And we had the linkage conflicts when we tried to link, generated SPIR-V. So in LVM IR, there is a link once attribute to a function, which allows you to avoid such kind of problems, but SPIR-V currently doesn't have it. So that's the way how SPIR-V could be improved. And we would love to use actually SPIR-V as the device code representation here and use SPIR-V linker to link device code, but currently that's not possible due to that problem which I mentioned. Okay. Then those BC files are passed to LVM linker. We get linked bitcode. After that, we pass it to LVM SPIR-V translator. We generate SPIR-V image. And this SPIR-V image is passed to this tool, which I mentioned, Clang Float wrapper, to generate object file, wrapping this SPIR-V image. And actually, this file can enclose multiple images, not necessarily SPIR-V. But currently it's SPIR-V only, yeah. So that was the device part of the compilation. Now, simple part is integration header generation. So it takes those source files one by one and generate integration headers where you have information about each kernel in your source, like what is the kernel name, a mapping between kernel name type, because SYCL actually identifies kernels by C++ type. It's very convenient because all the control for conflicts and so on is done by a C++ compiler for you. But that is not suitable for linkage, so we need to translate C++ type corresponding to a kernel to its name, to some string. And actually integration header provides that functionality. It maps the kernel type to kernel name as a string. And also provides information about what kind of arguments the kernel has and so on. So we generate two headers here, and then we have a host compile invocation, which also takes those sources, takes those headers, and produces usual host objects. After that, everything is linked together by normal linker, like platform linker, which is LD on Linux, or Microsoft linker on Windows. And we generate this final, what we call fat binary. Okay. So any questions? Yes? So on Windows, it doesn't work yet. We don't have Windows support yet. It's in the plans. So I will talk about this. But it is supposed to. So, but instead of LD, there will be a Microsoft linker, hopefully. Okay, so SYCL Runtime architecture. Basically, it shows, your host your SYCL application, which has host code and device code in it. You have here the SYCL Runtime library. You have here devices which you want to run on, and in the middle, lots of stuff. So the key point here probably is this SYCL Runtime plugin interface, which allows us to target many devices, even those which are not, which don't have OpenCL implementation. So yes, we designed it so that SYCL application could run not only on OpenCL devices, but on some other devices which have other runtimes exposing them. On CPU side, we use OpenCL runtime, Intel OpenCL runtime for CPU. And underneath it, it has thread building blocks runtime, which is used as a parallelization engine to run a SYCL program efficiently on CPU. Yeah, as you can see here, so there's a mechanism of plugins exposed by this SYCL Runtime plugin interface. This was derived actually from OpenCL with some additions, with many omissions, but it basically follows the OpenCL programming model, unless explicitly mentioned in the documentation. And so if you have some device which is not covered by OpenCL, you can write plugin based on this device runtime and still plug it into the SYCL runtime so that your SYCL program runs on that device. Okay. So more details about this SYCL Runtime plugin interface. So as I said, it is defined at the top of OpenCL programming model. So basically, this interface defines, of course, concepts like kernel, like program, like context, and so on. And it also divides a number of APIs, and most of those map directly to OpenCL, but not all of them. Some of them are new. And we use a similar mechanism to discover kind of SYCL, to discover plugins for SYCL runtime, similar to ICD discovery logic. So we intend runtime to be able to discover not only Khronos compatible OpenCL installations, but also some kind of custom OpenCL installations, not necessarily kind of installed on the system, but which are deployed in some directory or wherever else. And also, this discovery logic will be able to find plugins not based on OpenCL. Okay. So I guess this is the last slide of my presentation. This is future plans. So those are topics which we either work on already or going to work in some future. So in D-range subgroups, it's a feature to, to allow people to write in SYCL like they used to write in OpenCL for subgroups. Ordered queue, which I already mentioned, ahead of time compilation, scheduler improvements. So basically, currently, scheduler sometimes creates unnecessary data copies, which could be avoided. But yeah, so we're working to improve that. Unified shared memory is a great productivity feature, which allows you not to bother about memory management. So unified shared memory will do this management for you. You don't need to create buffers and so on. Yes.
Assuming that we can also share the pointer, right?
Yes.
Can you repeat that question? We have a microphone.
Yes.
So yeah, so assuming that you can share the pointers.
Yes, it assuming that.
Yeah, you don't need to transfer.
There are different kind of levels of this feature, and at the most advanced level, yeah, you don't even need to use special allocator.
Right.
Yeah, so it's very convenient. But yeah, it's evolving, and there is a documentation along with on the GitHub, so you can take a look at this. Hierarchical parallelism, which I mentioned, is also in the works. Generic address space handling. So basically, as OpenCL, SYCL defines certain address spaces like global, local, private, constant. But sometimes it's not very convenient, to manually track which pointer you have. And we think it is good to have this generic address space so that any pointer of any address space could be assigned to this pointer So it could basically represent any kind of pointer and let compiler figure out what specific kind of pointer it is. Windows support, as I said, specialization constant. So this is an OpenCL feature which is really convenient and important for performance in some cases. So we want this to be in SYCL too. We are going to make some documentation updates as well. Fat static libraries, I guess, are already there. And recently we came up with the need that we need somehow change how we distribute device code kernels per SYCL programs, per underlines, per vmodules actually. So currently what we do is all the kernels, so if you have an operating system module like executable or dynamic library, all the device code in it is put together into a single SPIR-V module. And if you have like 1,000 of kernels and you want to compile and invoke just one, it's not possible. You will have to compile to JIT compile all the kernels in the module because that's how underlying OpenCL works. So, and this is not very convenient for some of the HPC users. So we want to implement some kind of splitting this monolithic big module into pieces, more manageable pieces. Okay, that's it. So, questions?
So for SYCL, what kind of runtimes, device runtime do you support now?
Right now, we support only OpenCL underneath. So this plugin interface, which I mentioned, allows you to plug in basically almost any runtime, but currently we do support only OpenCL underneath us.
Okay, so for custom devices, the manufacturer has to provide that runtime, I guess. That's the
Yeah, so if you have already OpenCL implementation for your device, plugging it in should be like zero effort. But if you don't, then yes, you need to write a plugin.
For does it have a concept of resource sharing, so that if the device can support multiple applications, would SYCL be able, or it's up to the runtime to manage? Can you run?
Yeah, it's a good question actually. So resources, like you mean computational resources?
Yeah.
So if your device supports that, I mean, if there is an API which allows you kind of to fission your device, to partition your device into pieces, SYCL Runtime can take advantage of that. So in SYCL, you can create a device. You select your device using device selector, and actually you can implement the logic of how you handle this there. I mean, you can just, yeah, I think, so maybe it depends on how your runtime will expose those devices. Like you have your runtime and you ask, create a device. If it returns like entire device, then probably it can be used only in a single SYCL application. If you expose your devices like 4 virtual devices, then you can partition it, right?
In that case, then it would become like, are there APIs available for SYCL? So when there are 4 available, you can get 4. When there are 8 available, you can get 8. But then you leave up to looks like you leave up the device runtime to figure out, what's best. Although the device runtime doesn't know what your program is trying to do. Does it even need 8 or?
Yeah, right. So a lot is left to device runtime actually, and I don't know. You could use similar logic to like to affinity masks on CPU to control that behavior probably. So yeah, that part I don't think SYCL specifies anything of that. Andrew may correct me if I'm wrong. Okay.
So, does this work? I think in general, SYCL is sitting on top of OpenCL. So if you do these things in OpenCL, then the device gets exposed to it. Does that not work? So in general, SYCL is sitting on top of OpenCL. So if there's some low-level capability you need, like split up the devices, the device efficient, you can do it in OpenCL, and then you just provide that capability back to SYCL. Does that make sense? So even if SYCL doesn't have this feature, I think we probably don't, you just do it at the OpenCL level if you want that level of control.
It does, but then it brings it back to the question then why use SYCL if I have to do all that work anyway to get the fonts out or specific feature out. I can write as well in my
I mean, I think you're using SYCL to be able to write complex C++ software, right? If you're doing something specific to just say, right, just create this device on, because it's going to be quite device specific to say run this device on this platform.
I'm kind of hinting at how to get a more performance portability, right? So SYCL does give portability, but how to get, so this was one of the features that we would want to get specific device performance to be able to do something special like this. But if anything special is we have to do custom stuff, we have to expand your OpenCL runtime to do anything. The value of SYCL becomes like
I think the value of SYCL is that it allows you to do kind of performance portability techniques at a higher level. It's a kind of way of getting up to a higher level of programming where you can do the performance portability. But I think as a programmer, if you're faced with a problem, you're faced with a device where you want to have the ability to, whatever it is on that device, you're drilling through all of that abstraction, but you're only doing it in one part of your program. So in one part of your program, say, well, I want to be able to drill through that abstraction and say, do that specifically on this device. And what SYCL is allowing you to do is to do that only in one place.
But he also wants to abstract the device architecture away from the program, so he only deals with the in an abstract form that the device has certain capabilities available. He doesn't have to really figure out what slices are available at what point in this application. Sometimes
Yeah, I don't know. I suppose at a high level, the philosophy of SYCL is like the philosophy of C++, right? So you have all of these abilities to abstract things and write complicated software, but if you want to just drill down through the whole thing, you've got that ability. So you can use the OpenCL features or the intrinsic functions or whatever it is. So I mean, from my point of view, if I'm a developer, I want to build up a big complicated C++ application and run lots of stuff and integrate it stuff together very well. But then if I'm faced with a problem, I need to optimize this, and I know the hardware does something that I know I need to do, I don't want to be blocked from drilling straight down. I just want to be able to just do that job, get it done, use that hardware capability, and the whole of the rest of my application should work. That would be the philosophy that I'd seen it. Yeah.
Okay, thank you, Andrew. So with this, I conclude my presentation. So thank you, everyone. I think I will be available for questions after this talk.